Alright, hello everybody. Welcome to the OpenRocket training series. And in these videos, we're going to learn how to use OpenRocket to design rockets, select motors, and simulate how those rockets are expected to perform. And rather than just going through the slides, I'm also going to work directly alongside you all in OpenRocket so you can become familiar with the different tools and settings that are located within the software. So for this first video, we're mainly going to focus on the basics of OpenRocket and the Rocket Design tab. So let's go ahead and get started, and let's start with the warm-up question. Why should we simulate a rocket to begin with? Well, there are a lot of possible answers to that question, but the main reason is that simulation allows us to test our designs before committing time and material to actually building it. From that, we should hopefully be able to identify any problems in the design, or just compare different designs that we've come up with and make predictions about how those rockets should perform. Now, what is OpenRocket? Well, OpenRocket is a design and flight simulation program. It allows us to create the digital models of our rocket that the models will use to predict things such as stability, altitude, velocity, acceleration, and recovery performance. And the important word here is that it is a prediction. The models that OpenRocket gives us are just estimates of what our rocket should do based on the information that we provide, but we can then later verify that information and expectations from the physical test flights that we will do with our rockets. So really quick, I'm going to go ahead and switch over to the download section on OpenRocket's main page. So on OpenRocket's main page, you can download the different versions, the latest versions, including the Windows application, which we are going to use today. And from there, I will go ahead and pull up what OpenRocket looks like when you open it for the first time. So it's going to be a little confusing. However, OpenRocket is actually quite simple. There are 3 different tabs that we're going to look at, but in today's video, we are just going to stay on the Rocket Design tab. And from there, we are going to build a mock rocket and show how to use the different tools within this section. So in Rocket Design, what we are trying to do is actually create the physical model of the rocket itself. And we can do that by adding in different components. So to start, we're going to start with the nose cone. That is one of the 3 options we have when we are on the sustainer section. So we're going to start with the nose cone. I'm just going to leave everything default for now. I will then add a body tube, and we'll throw in some fins. And there you go. There's your rocket. But not actually. We haven't really finished the full design of the rocket. This is just a very simple model, but we have no motors, no parachutes, no mass components. So let's start adding some of those in. From this section, by clicking on one of these parent components, such as the body tube, we can then add dependent components, or as they are listed here, inner components or mass components. And so we're going to go ahead and add an inner tube. Now, traditionally, this might be the tube that the motor sits inside of, just because sometimes the airframe is larger than the motor is of the rocket. And we're just going to leave everything default for now. But you can see with all of these components, you can typically adjust things such as length, diameters, wall thicknesses, what the material is made out of, and its relative position within inside a component. So for instance, in this body tube, our inner tube is relative to the bottom at 0 inches. Looks to be accurate. If we changed it to the top and set this to 0, we can then see it changes that location. So let's go ahead and just set that back to the bottom. I liked where that was at. And we're going to go ahead and say that this component is a motor mount, because that is what this tube is going to function as. So we're going to go ahead and click OK. Okay, so we've added that component. Now let's say that we have a mass component, and it's going to be in the nose cone this time. So we're going to go ahead, click on the nose cone, click on mass component, and we could give it a name such as payload. This payload is going to have a mass of 0.25 pounds, and we're not going to change any of the lengths, but we do want to change the relative position of this payload. So I'm going to go ahead and set it to middle of the parent component, set it to 0, and there it has adjusted it for us. I'm going to click OK. Okay, so we have done that, but now looking at my rocket, I'm going to want to go ahead and change the fins. And so I'm going to go ahead and click on our freeform fin set, click Edit, and now we have this section here. I'm going to change it to 4 fins. I'm going to change the shape of the fins as well, and you can see this just lays out a X and Y coordinate system. So for now, I'm just going to change the the Y position to 2, this one to 2 as well, make this one 1, just make them nice and simple. Let's go ahead and change this bottom one to 8, and do not worry about this in just 1 second, we will change that. Okay, so we're back here, wanted to change this value to 6, go ahead and change this value to 5, and this is a pretty simple trapezoidal shape. The fins are a little bit large for our rocket currently, but we should be okay just to leave it there for now. So let's go ahead and go back to general, and we need to adjust the relative position. As you can see, our fins are hanging off the end of the rocket. That is not what we want. So we're going to go ahead and set this bottom relative position back to 0. It'll adjust that for us there, and then we can go ahead and click OK. Alright, so now let's say you were making your design and this is not exactly how you wanted your rocket to look. So we can go ahead and just change these other component lengths. Let's go back to our body tube, and let's change the length of this to 14 inches. Now let's say also here we decided, well, the diameter is going to be a little bit larger than we expected. We currently have it set to just under 2. Let's go ahead and say the outer diameter is 3.1. Okay? And now it's really starting to mess things up, but that's okay because we can go back to all of these components and change things as necessary. So you're never in trouble if things start looking somewhat odd or you get warnings. You can always go back and change some of these, and we're going to show you how to do that here. So the wall thicknesses will automatically adjust the inner diameters. If, for instance, we change this to 0.1, you can see it adjusts there, and vice versa. If we change this value, it will adjust this. So always just be cognizant of that when you're making these changes. And we will leave the component material as cardboard and click OK. So the reason why we're getting this warning is because we have a discontinuity in diameters, because we just adjusted the body tube without adjusting the nose cone. So let's go ahead and change that base diameter to 3.1. We'll also adjust the wall thickness just to be consistent, and we will also change the length of this to 8 inches. Okay. We need to change our motor tube as well. It's looking a little bit small now. So let's go ahead and change the outer diameter. I'm going to use a different unit here just because this is a motor size that is fairly relative within rocketry. We'll also change this to 6 inches, and everything can be left as cardboard, and we'll click OK. Okay. So now that we are here, we need to actually start thinking about how is our rocket being put together. Because right now, while this looks appropriate from a model point of view, this does not actually describe how our rocket is going to be put together. And what I mean by that is your nose cone. Is your nose cone just simply sitting on top of the body tubes, or is there some type of interface that is allowing those two to connect? And we can actually go onto our nose cone, and in a pre-built section, we can look at shoulders. So for instance, we know that the inner diameter of our body tube was set to 2.9. Go ahead and set that, and we'll set a length of 4 inches. And now what you can see here is that we have basically inserted this shoulder section that we can then model, and also changes the mass of this nose cone to more accurately reflect how this nose cone would be situated inside of a body tube. And we can also take that same concept and apply it to different body tubes. So let's go ahead and add a new body tube. And as we can see here, it decided to put it at the back of the rocket. Not exactly what we wanted. So we're going to go ahead and drag this body tube up to just under the nose cone. And now it is positioned relative to just underneath the nose cone here, in between this other body tube. So we're going to do the same kind of concept here. Just going to change some lengths, make it just a little bit longer. Component is going to be made of cardboard. That is fine. It auto-filled the diameters already, so that's not necessary, although our wall thickness was not adjusted, so we did that manually here. And we will go ahead and click OK. Now, from this concept, we're going to go ahead and take this same body tube, and we are going to add a tube coupler. These are just presets that you can use. We're not going to use any presets in this video today. And so what this has done is has inserted a coupler between these two body tubes. And when you think of how different sections of a rocket are going to go together, they need to have some type of material to interface with. And by that, this coupler should sit relatively in the middle between these two tubes. Now, of course, this length is a little bit small. We'll make it 4 inches, and then make it 2 inches to the right from the bottom of this parent component. And now this more accurately reflects how these two body tubes would go together. This coupler would be permanently attached to this body tube, whereas this interface would be non-permanent. It would just be friction fitted. So you could put the two sections together, pull them apart, but this coupler will always remain attached to this body tube. Okay, now that we've thought about the interfaces between different components, we now also need to think about how we would attach different hardware or other components to our rocket. And now we're going to go ahead and look at the fins. So on the body tube, we can also add centering rings and bulkheads. And this will be important for our fins in particular. So to do so, we need to add centering rings. Let's go ahead and add that. We will make the thickness a little bit larger so we can see it. And we're also going to change this to birch as well. So we'll just click OK. Now a neat trick you can do is on one of your components, you can go ahead and click Control V on the keyboard, and you can paste that as many times as you'd like, and then we can just move these components by adjusting its relative position. So I will go ahead and actually move that a little bit more forward. We'll take this centering ring and we'll move it -4 this way. We'll do -6, I believe, is going to be perfect for us. Yes, that's great. And then we're going to click OK. Now, the way we have this rocket currently set up is that these fins are purely attached to the side of the rocket. Now, traditionally, in rockets of this size, that is not how we're going to attach the fins. It's just not a lot of surface area for any epoxy to attach the fins to the body tubes, and it's a very weak joint. So what we can do is we can actually model that there are fin tabs that are going through the airframe and are touching this motor tube. So we're going to go ahead and do that by creating these fin tabs on our fins, and we will adjust the height to just under 1 inch. I think will be perfect. Yeah, so 0.9 inches in this case for us. And it has built these rectangles here to indicate that the fin is not just this trapezoidal geometry, but it is also this rectangular geometry as well, and it is all one piece. And what that does is that it also changes the mass component of this fin and all 4 fins. And so that becomes super useful as we are trying to model our rocket. We need to be sure we are accurately modeling every part of our rocket. So if the nose cone happened to change shape or size, we would want to accurately reflect that as well. And so let's just go ahead and say that we decided that we wanted to do a conical shaped nose cone. And now that is the shape of it. We'll click OK. And from there, we just need to do some final refinements, such as let's go ahead and increase the length of this tube. We'll do, 9.5 inches is fine. And the reason that we're doing that is because this centering ring here at the top is actually where we're going to have hardware to attach parachutes and shock cords to. And if you're wondering what that looks like, there will be some other information about that, but basically if you looked up something like an I-bolt or a U-bolt, that would be typical hardware you would see to attach a parachute, just some type of metal bracket basically that you could attach it to. And to simulate something like that, we could always just add mass components and change the relative position to roughly where the attachment would go. And if you wanted to get fancy, you could even change the radial position to reflect where it is in the rocket, and maybe even change the shape just slightly. Maybe not that. Let's do 2 inches long and change the diameter to 0.5. Yeah, and now that's looking pretty good. That can indicate our I-bolt mass, and we could always change the mass to more accurately reflect that. So there we go. We've done that, and so from there, if we wanted to add any other components such as parachutes, we can go ahead and add those parachutes. Those diameters will be given from the parachutes in your kits. So in this case, 36 inches is a pretty common parachute size. We will change the relative position to sit within this body tube, and when you pack a parachute, it will typically have a packed length and a packed diameter. So we'll just go ahead and increase that to more accurately reflect what it will look like. Okay, so from there, let's go ahead and take it back, look at the slides, and let's see where we are within rocket design. So far we have covered most of this basic information of working within the rocket design tab. We've added nose cones, body tubes, fins, some internal components, recovery components, and mass components. You can see here in this rocket design we had a scientific payload, and we were able to set those masses and its relative position within those body tubes. We have not fully looked at this yet, so let's go ahead and do that. I can actually go ahead and pull up this same model for you. So here is that model that we are working on. And what we had done there was we had changed the relative position of the fins. All right, so let's go ahead and do that, and then say it's actually from the middle component, and we'll change it to 0, something like that. We're just moving it just to show you what is changing. So mainly what we're looking for when designing rockets are going to be these 3 different sections here. They are the basic dimensions of the rocket, including its length, diameter, mass, and mass width motors, the flight configuration, and the stability. Now, in most cases, if you haven't actually assigned a motor configuration, you will not have all of this data, as shown in our other design. No motors, we have nothing here. Mass with no motors, there is no mass with motors because we have no motor assigned, and then we have a basic stability margin there. But we can see here when you actually do have this full configuration, this is all the data that you are looking for. And the point that that previous slide was trying to make was that if your stability goes below 1, in this case we're actually almost at 0, your rocket becomes unstable, and that is material that is covered in the rocketry fundamentals section. So let's go ahead and change this back to 0. As you can see here, a stability of 1.69 calibers is good stability, and that is based off of the location of the center of gravity and center of pressure. Now back to our rocket design, we can see here currently we have a stability of 1.56, but it is important to note we do not have nearly as much information as this other design does, including we do not have a motor selected, and we do not know the final configuration of what our rocket design is going to look like. So always tread lightly. Just because your design seems to be stable in its current configuration, sometimes when you add motors, different motors of different sizes will have different masses, and based on their length it can change the location of your center of gravity. So you may have to go back and evaluate your design, maybe change the shape of the fins to be larger, maybe make them more swept back, or extend the length of your rocket in total. So as a recap, we have covered all of the material that is laid out for the OpenRocket basics and the rocket design, and moving forward we will talk about how to select a appropriate motor and then what to look for when we are actually finally looking at a design for our rocket. So